सनत कुमार सुरेश नायक दिजन कर्तव्य कौन रजिस्ट्रेशन करते कौन रजिस्ट्रेशन कर देख
द्वारा डायल करा जायथिबा नंबरटी वर्तमान व्यस्त अछि दयाकरी किछि समय परे डायल करंतु आपके द्वारा डायल किया गया
फोन करथिले कोइ नेट पाउनु जॉइन करथिले मैडम फोन करथिले
आपण जो व्यक्ति को कॉल करूछथि से उत्तर देउनाहंती दयाकरी किछि समय परे चर्चा करंतु आप जिस व्यक्ति को कॉल कर रहे हैं वह उत्तर नहीं दे रहा है कृपया कुछ समय पश्चात कॉल करें The person you are calling is
Hello. হ্যাঁ প্রফেসর দে জয়েন করুন, উইল স্টার্ট। ওকে, দেখতে পাচ্ছি না আপনার ইয়েটা। হ্যাঁ বাস ঠিক আছে। Very good. So Professor, they actually will start. Okay.
Yeah, sure, sure.
And I think others actually will be joining slowly.
Okay.
So a very hearty welcome to the 68th distinguished lecture that is being organized by INA Bhubaneswar chapter, IIT Bhubaneswar, SOA University, IMMT Bhubaneswar, neither Bhubaneswar, then ICT IOC campus Bhubaneswar, IEEE Bhubaneswar section. So it is indeed a great pleasure to have with us sorry. It is indeed a great pleasure that we have with us Professor Sishendu De, a distinguished professor of Department of Chemical Engineering, Indian Institute of Technology, Kharagpur, to give his lecture today. We are really fortunate to have him. And his topic is going to be in-house scalable low-cost technologies for water treatment. I'm not really going into details of his topic, but a short abstract which he has sent, I'll just read before you. With the ever dissipation of natural resources, the technologies with zero discharge are in high demand. However, if such technologies are imported, they are expensive. On the other hand, the efforts of the researchers should be directed to develop indigenous technology that has advantages like scalability, economic and technical viabilities, easy operation and maintenance. In this talk, he is going to discuss some of these technologies in detail, including the treatment of groundwater and industrial wastewater. The groundwater treatment includes the removal of arsenic and chloride. The wastewater treatment involves the treatment of the effluent generated from rice mills, effluent, cyanide removal from the steel industry effluent, organic removal from the refinery effluent, etc. A detailed description of these technologies, lab development, scaling up and deployment in the field will be all discussed by Professor Day. So far as Professor Sishendu De is concerned, he is a BTech, MTech, and PhD from Department of Chemical Engineering, IIT Kanpur. His main research interest includes membrane separation, membrane casting and application, water treatment, modeling and design, transport in microchannels. He has authored 8 books, 21 patents, 383 publications in journals of repute with H index of 71, handled more than 50 research projects and transferred 6 technologies for commercialization to 11 companies. He has guided 32 PhDs and 60 plus MTech students. Professor Day has been awarded several awards, including Institute Chair Professor 2020, Abdul Kalam Fellowship for Innovative Research 2017, INA Chair Professorship 2015, Santi Swarup Bhatnagar Prize in Engineering Science by CSIR Government of India in 2011. He is the Fellow of Indian National Academy of Engineering, the National Academy of Sciences, Allahabad, Indian Academy of Sciences, Bangalore, and very recently he has become Indian National Science Academy Fellow. And I am really proud to have such as a distinguished personality as one of my colleague in IIT Kharagpur. He is the founder of the spin-off company Majors Technokeeps Separation Private Limited. Very few people actually who have their spin-off companies, and Professor Day is actually one of them. With this brief introduction, I will now request Professor Day to please make his presentation. Professor Day, please.
Yeah. So I'll be sharing my presentation. Is my slide visible? Is the presentation visible?
Yes, sir.
Hello?
Yes, it is visible.
Yes, visible, sir.
Okay, sure. Okay, thank you very much, Professor Acharya. At the outset, I would like to express my thanks to Professor Acharya to invite me in this forum to give a presentation. And I'm really indebted to him for various opportunities that he has provided during when he was the director at IIT Kharagpur that time. So he provided lots of facilities to my research, so that the research has come to of my laboratory has come to this stage now. So I'll be presenting some case studies where we'll be talking about the generation of scalable low-cost technologies for water treatment, and how the technologies have been developed in the laboratory and put into the real plant scale. Okay, so first case study, I'll be talking about the removal of arsenic from groundwater. As we know that arsenic, in the presence of arsenic in the groundwater, it causes various diseases like cancer of bladder, lung, skin, etc. But mostly it is manifested in the skin cancer, and this is known as the disease is known as the arsenocosis. And there is no remedy of arsenocosis. Only the doctors prescribe some protein-rich diet so that the immunity power in the body increases. The typical WHO limit of the concentration of arsenic in the groundwater is 10 microgram per liter and less. And typically in various places of India, we find a concentration anything between 50 to 600 microgram per liter level. So that is the extent of contamination of arsenic in the groundwater. So if you look into this chart, if you look into the chart of India, all the states starting from Punjab, Haryana, Uttar Pradesh, Bihar, Jharkhand, and up to West Bengal, along the Ganges, the states have been, the groundwater have been contaminated by the arsenic contamination. Now, if you look into the state of West Bengal, all the 7 districts along the Ganges, the groundwater is polluted by the arsenic. If you look into the plains of Bangladesh, the Bangladesh plain, it is the Brahmaputra river, and it's 2 sides of the Brahmaputra river we have the arsenic contamination. So basically what we find is that if along the river banks like Ganges and the Brahmaputra, there is the arsenic contamination in the groundwater. So let us try to find out why only these areas have been adversely affected, because the lands are very fertile along the rivers. So there are lots of agricultural activities and human activities. Typically, arsenic is bound to the rocks in the form of arsenic, aluminum. There are aluminum and iron components are there in the rocks. There is a geogenic cause, and these two materials are strong binders of arsenic. So arsenic is generally bound to the rocks in the form of iron arsenic and alumina arsenic bonds. So now whenever there are, because of the runoff water, sometimes these bonds break open and arsenic get released and come to the groundwater. In the fertile land, there are lots of agricultural activities are there. So there are lots of fertilizers people use, and one of the typical fertilizer is phosphate fertilizer. This particular radical is the culprit. Whenever it flows off through the runoff water, whenever this phosphate radical faces arsenic iron and arsenic aluminum bonds, these bonds break open and arsenic get released and come to the groundwater. Because of the bacterial activity from the human waste and animal waste, this arsenic, that is those are bound to the rock, they also get released and come to the groundwater. So there are 3-4 postulates by which the arsenic from the geogenic cause and anthropogenic causes are there, for which the arsenic that is bound to the rock, they have been released and come to the groundwater, and this particular and contaminates it. So this particular phenomena, and that is why the river banks, the groundwater in the river banks have the more arsenic concentration compared to the inland. Now, if you look into this release of arsenic from the rock, the procedure and mechanism, whatever I have discussed in couple of mechanisms, this is occurring since last million of years. So slowly the arsenic concentration in the groundwater increases. And because of the earlier, there is a, if you look into the rain pattern, there is a distinct change in the rain pattern. Nowadays, the rains are not falling uniformly throughout the whole season, but it is concentrated, on very few hours or very few days. So the rain, since the rain fall is very, it is not uniform. The groundwater recharging is not uniform, and it is not complete. So level of water deplenishes, and therefore the concentration of all these inorganics like arsenic, fluoride, lead, etc., those are there in the salt, those are there in the groundwater, they get concentrated. So this whole thing is happening since last 70 years, where the rainfall pattern is changed in our country. So arsenic contamination, and we are really unlucky that since 1980s, some of the places the arsenic concentration has increased beyond the WHO permissible limit, 10 microgram per liter. So the first arsenic was detected in state of West Bengal back in 1982, when in a particular place in South 24 Parganas district, the arsenic concentration has been detected, which was around 70 microgram per liter. Then from the same source, the concentration has increased to 250 microgram per liter in the year 2005. So that is the way, or the rate of increase of arsenic contamination in the groundwater at the same location. So, but if you look into these 3 districts of the southwestern part of West Bengal, the Midnapur, where the IIT Kharagpur is located, Midnapur, Purulia, and Bankura district, we do not have any arsenic contamination in the groundwater. All the river banks, we have the arsenic contamination in the river, in the groundwater. Okay, so we started to look into this problem back in 2004. Why this thing is happening? That in some places arsenic contamination is not there. In some places, typically the river banks, we have the arsenic contamination in the groundwater. We have ultimately identified is the nature of the soil. If you look into these three districts are the eastern tips of the Chotanagpur Plateau. So the soil is not fertile alluvial soil. The soil is hard rock-like soil. It is a red soil. It is called lateritic soil. This is a laterite soil full of, it contains lots of aluminum and iron oxides. So therefore its color is red. So and as I said earlier, that iron and aluminum, they are the potent absorbents for the arsenic. So Mother Nature has already given us a protection in these 3 districts, where we have a natural protection from the arsenic contamination in the groundwater. In fact, that is the reason why these three districts we do not have any contamination of arsenic in the groundwater, but the other districts we have the arsenic contamination in the groundwater. So we started to look into the lateritic soil. It is commonly known as moram, and typically this particular soil is used for the land filling purposes. It's used for the road laying purposes. This is available in the form of big chunks of boulders. Then what do? We then pulverize it to a particular mesh size. So what is the different, we have all looked into the various characteristics of this soil. So this particular soil has, since it contains iron and aluminum oxides, they have the natural capability for both species of arsenic. By the way, arsenic occurs in two forms, arsenic 3 and arsenic 5. In a typical groundwater, fresh groundwater, arsenic 3 content is around 80%, 20% is arsenic 5. But when the water comes out, there will be the aerial oxidation, and arsenic 3 is converted to arsenic 5. Both the forms of the arsenic are lethal, so therefore one has to remove both the forms. So the raw laterite itself is having some arsenic removal capacity, however low it is. Then you do some chemical treatment. I'll come to the chemical treatment later on. We do the chemical treatment of the raw laterite and increases its arsenic removal capacity several folds. And we have found out the total removal capacity of arsenic is 47 milligram per gram. Then arsenic concentration can be brought down to less than 10 microgram per liter. That is the ppb level. That will be the limit set by the WHO. And another striking feature of the lateritic soil is that it is having strong antibacterial activity. It is antipathogenic property is there. So it has a better antibacterial property compared to silver oxide impregnated carbon. The filter that you have developed based on the treated laterite, that can be scaled up to any scale between 500 to 1,50,000 liters per day. For the domestic filters, we do not require any external power. Since the arsenic capacity is removal capacity is pretty high, 47 milligram per gram, the nearest competitor for that to the laterite is the activated alumina, and activated alumina has a capacity around 10 milligram per gram. So we have almost five times more capacity compared to activated alumina. Since its capacity is high, its life is pretty high. One can have a filter life to 5 to 7 years depending on the concentration of arsenic in the feed, and we do not require any regeneration during its lifetime. And we have also calculated the economics. The economic comes out to be pretty low, 1 paise per liter. And the most striking feature is that this particular material satisfies the TCLP protocol. That means whenever I'll be just after its life will be over, this material will be can be used as the road laying purposes. And one or a road or a land filler, we do not require any special treatment. There is no interference from the competing ions like sulfate, chloride, magnesium, iron, etc., which are observed in the groundwater, and it can work over a range of pH 5.5 to 8. So if there is a groundwater which has a slight fluctuation with the pH, this material can work. Okay. Some of the this slide presents the mechanism of arsenic removal using the lateritic soil. The mechanism is by chemisorption and the ligand exchange or ion exchange. So therefore, the arsenic is absorbed in the in the lateritic soil by replacing hydroxyl ion, as has been shown here, and certain cases they have been absorbed on the metal sites by strong chemisorption. Now, some of the technical terms, information I would like to present here. This XRD figure shows that there is in the raw laterite there is presence of iron and aluminum compounds. So the iron and aluminum phases, those have been identified in the XRD of the lateritic soil is iron, silicon sulfide, magnetite, hematite, iron oxide, geothite, iron silicon, aluminum oxide. So therefore, these particular phases of the iron and aluminum, they are the potent absorbent sites for the arsenic. And raw laterite itself has some arsenic removal capacity, however low it is. As I said earlier, it is having a total 0.8 milligram per gram of total arsenic removal capacity, although it is less. So what we do, we do a chemical treatment and increase its capacity several folds. So now one can ask that, how do I find out whether the lateritic soil that I am going to get from our Kharagpur area, or from the Deccan Plateau, or from the in Madhya Pradesh or Maharashtra, whether that is good enough for the arsenic removal or not? For that, we define a scientific quantity that is known as the degree of lateritization. What is degree of lateritization? It is a ratio of silicon divided by iron and alumina. More with the silicon in the material, less highly brittle it is. So more with the iron and aluminum oxide are present in the material, better it is for the arsenic removal. So therefore, this the degree of lateritization should be less for a desirable material, which is a potent source of adsorbent for arsenic. So we have calculated the SS ratio, the degree of lateritization, for different locations like Kharagpur, Bankura, and Purulia district, and we have found out that is the minimum around 0.42 to 0.5 between Kharagpur and Bankura. So Kharagpur and Bankura laterite are the best among the four. So if you give me a material which is available from any part of the world, we will just do an EDX analysis that will take 15 minutes time, and we just find out what is the degree of lateritization. If it is less than 0.4 or 0.5, then it's a very good material for the arsenic removal. Then we'll do a treatment. As I said, that the raw laterite itself is having an arsenic removal capacity of 0.8 milligram per gram. Now, what we do a simple chemical treatment. By a simple chemical treatment means, first we treat it with a dilute sulfuric acid, hydrochloric acid, and this acid will clean up the material and make it more porous. And then, but during the acid treatment, some of the metal sites like iron and aluminium, they get dissolved chloride and they'll be leaching out. So then that's why we do the alkali treatment. During the alkali treatment, the metal hydroxides will be formed, and the nascent metal hydroxides will be deposited on the particles of the laterite, and some of them will be diffusing inside the pores, increasing its capacity several folds. So by doing this simple acid alkali treatment, we increase the capacity of the arsenic removal capacity from 0.8 milligram per gram to 47 milligram per gram of the total arsenic. What acid alkali treatment does, it increases the surface area. That means it increases the porosity several folds, from 1.015 to 0.1. There is an order of magnitude increase in the porosity and the specific surface area. Now, in this slide, in this table, I have presented that whether what is the effect on the property if I go for a production of a small scale or a big scale, because we have to produce in tons, because if you like to commercialize and go for the community waste filters. So we have shown that it's treated the property of the material with a 50 gram batch and with a 1.5 kg batch, and both all the properties in both the batches are quite close. Now we look into the disposal of the spent material. That means when the adsorption is over, it satisfies, as I said, it satisfies the TCLP protocol. That means it is after its life will be over, the material is exposed to harsh pH conditions, low pH as well as the high pH. In both cases, the leaching of the arsenic is minimal and it is below detection level. So therefore, there is no special treatment required for the disposal of the spent material. It can be directly used as the road fillers or the land fillers. It can be used as one of the piling material in the preparation of the pavement block. Now we come to the detailed design of a single unit. The single unit here I have shown, it is a composite bed prepared by raw laterite at the top of the bed, which will be removing arsenic to some extent, then followed by a charcoal. It's basically activated carbon, and this carbon will be removing the ordering material and the organics. Then the treated laterite bed, which removes the bacteria as well as remove the arsenic. And there is a bacteriostatic carbon that is placed at the bottom so that the bacterial contamination from the bottom is prevented. Now, before putting this unit, one has to do an one has to install an upfront unit for the removal of the iron. So for this, all these filters which are basically working with the adsorption principle, there is an upfront unit for the removal of the iron. Otherwise, the iron will be in the long term, the iron will be deposited in the actual filter, and the filter will be completely blocked. So iron is removed, followed by the arsenic and the bacteria. And this material is also very good for the removal of the heavy metals. Now we look into the design. So there are two types of design, one by heuristic, another by the going the fundamental principles. And the advantage of the fundamental physics-based principles is that it can withstand all sorts of fluctuations of the operating conditions. So here we have used these two performance parameters, governing partial differential equations, which will be representing the transport phenomena inside a particle and the transport phenomena occurring, that is inside the fixed bed, in this bed. And we have developed this performance curve. This performance curve is generated for the y-axis, it is time, that means it's life of the filter. In the x-axis we have the flow rate, and for different concentrations, fit concentration of the arsenic. So if you have an arsenic concentration of 70 ppb, 70 microgram per liter, and if you are talking about 100 liter per day flow rate, then the life of the filter will be around 1200 days. That is close to 4 years, right? 4 years, close to 4 years. So one can really design a particular filter and can generate, can predict the lifetime of the filter. Since its capacity is high, during its lifetime, one need not to go for a chemical induced regeneration. So some of the snapshots of the filter. So these are so as I said, the first filter we have the work we have started in 2004. Then we gave lots of presentation to arsenic task force, government of West Bengal, and ultimately UNICEF came to us, and we put up a community scale filter in an affected school in Rajarhat area, where the arsenic contamination was around 100 microgram per liter. So this is the school where this capacity of the filter is 500 liter per day. There are 70 students, around 20 more, around 25 more, staff members, teachers, and the midday meal ladies and cleaners, etc. So out of 500 liter per day, 250 liters is used for the cooking of the midday meal and the drinking purpose. Rest 250 liters is used by the villagers. There is a tap outside where the villagers used to take the water. So this filter was so this is the performance of these filters. If you see this data is for 6 years, the data 2012 to 2018. The left hand panel we have put the arsenic concentration, in the right hand panel we have put the iron concentration. If you look into the arsenic, the black dots are the concentration in the feed, the red dots are concentration in the filtrate. So if you look into the black dot, it varies from 50 to 225, 230 microgram per liter level in certain time. There is a seasonal fluctuation during the summertime. Because of lack of rain, the concentration shoots up and the concentration of arsenic increases. During the rainy season, because of the dilution, the concentration goes down. But if you look into the filtered performance, the red dots, the concentration is always below 10 microgram per liter, and there is also fluctuation, but it is well within the safety limit. Then if you look into the iron concentration is sometimes is very high. It changes from 1 ppm to milligram per liter is ppm, 1 milligram per liter to 30 milligram per liter. But if you, and the concentration of iron, acceptable limit is 0.3 milligram per liter, and it is mostly below 0.3 milligram per liter. If you look into the microbial removal performance, typically the WHO limit is that there will be no microbial, no bacteria present in the drinking water. And although the various filters, they claim 99.9% removal, but there will be some finite amount of microbes still remaining in the final filter. But in our case, we have found out that in the filtrate, the bacteria concentration is below detection level. Some of the domestic filters that we have deployed in various places. Now there are more than 50 numbers of places have been we have distributed in various districts as well. So here, if you, I have just given an example. This is a lady in whose house this filter was deployed. So in this filter, it's a hand-operated filter. There is no electricity required for this household filter. On the top bucket, we just put the water. There's a pinch cock here that controls the flow rate of water into this filter body. In the filter body, there are different layers of the material, as I shown earlier, and the water gets filtered and it comes to the ground. There is no wastage of water like the RO filter or something. Okay, so if you look into the performance, this is 3 years performance, 2012 to 2015, and the concentration of arsenic in the feed is around 100, 200, in sometimes 300 ppb, but in the filtrate it is always less than 10 ppb. If you look into the iron concentration, there also the concentration can be as high as 4 to 5 ppm, but the concentration of iron in the filtrate is less than 0.3 ppm.
Oi.
Some more community scale filters that we have deployed in different places, like Ambika Girls School, there is 1500 liter per day capacity. It is deployed on in 2013, where the inlet concentration was 290 ppb, filtrate is 2 ppb. And similarly in Malda Rotua Block 2, it is also sponsored by UNICEF. No, so after, basically, then we got the approval of recommendation from the Arsenic Task Force Government of West Bengal after showing these results, and then technology was transferred to 3 companies. By now, one of these 3 companies, one company is basically a vendor from the government organizations, the Public Health and Engineering Department, and they have deployed more than 550 filters of 2 meter cube per hour capacity in West Bengal and Assam. This company, Ranchi-based company, they have deployed community scale filters in different places of Jharkhand, Bihar, and UP. This company, they sell the domestic filters. They have deployed more than 100 filters in different affected areas. This is one of the community scale filter of 2 meter cube, 2000 liter per hour capacity. Typically, these filters runs for 5 hours a day, producing 10,000 liter of water, catering to a cluster of villages. So this is one of the place that is in Nadia district, where the concentration in the feed is 110 microgram per liter, and the filtrate it is below detection level. Similarly, the iron. These are the there is a solar power. So there is a solar panel that pumps the groundwater and takes it up to the overhead tank, and from the overhead tank it flows by gravity, flow through the filter columns, and finally it gets the filtered water. So this is a test report of the government Public Health and Engineering Department's test report. So every district there is a test house formulated by the established by the Public Health and Engineering Department, Government of West Bengal, and the performance of our filter are monitored for every month. And this is one of the typical results that have been shown in the test house of the Public Health and Engineering Department in the Barasat district. Okay, so it is not that we bring the samples at IIT and then we measure. So the performance of the community scale filters are continuously monitored by the state laboratories. So what are the let me talk about the elements of innovations in this technology. This is a low cost technology without compromising the quality of the material. So therefore, if you look into the material cost, the cost of the laterite will be 100 rupees per kg, okay, including electricity, utilities, and the labor, etc. But comparatively, the cost of activated alumina, which is a synthetic material, it costs around 250 rupees per kg. The design is that since it has a very high capacity, it has a long life, 5 to 7 years. Then we have the value addedness. It removes iron, bacteria, and arsenic, all the 3. And it also removes the heavy metals like lead, uranium, zinc, cadmium. There is no regeneration required during its lifetime. Therefore, the maintenance is minimum. And there is easy disposal. Since it satisfies the TCLP protocol, we do not require any special treatment for the disposal of the treated material, of the spent material. So this is the status of technology. It is shortlisted as one of the top 4 technologies in Reed Elsevier Environmental Challenge in 2015. It is a finalist of the Dhirubhai Ambani Prize in 2016. We got the Indian Desalination from the Indian Desalination Association, the Innovation Award in 16, Hindustan Door Oliver Award from IICHE in 2017, NRDC Award in 2017. This technology is recommended by the Arsenic Task Force, Government of West Bengal, as well as the Mashalkar Committee recommendation we received from Ministry of Drinking Water and Sanitation, Government of India. It has been rated as 100 best innovations in India in 2021 by Indian Innovators Association. It has transferred to 4 companies for commercialization. 550 community scale filters are now installed at different places of India, catering to about 8 lakh people per day. Next case study, I'll be talking about the fluoride removal filter. Similar for like arsenic, fluoride poisoning in the groundwater is also a rising concern. Like the disease caused known as the fluorosis. There are 2 types of fluorosis. One is dental fluorosis and is the skeletal fluorosis. And excess use of the fluoride in the groundwater, what it does, it basically weakens the bone. So there will be for dental fluorosis, there will be yellow stains on the teeth, and it spoils the early years. In case of skeletal fluorosis, it is even more dangerous. The bones get weakened, and these will really cause an early onset of osteoporosis. 200 million people have been affected in 25 nations, and 11 states have been affected in our country, including Telangana, Andhra, Rajasthan, Gujarat, Punjab, Haryana, and 4 districts in West Bengal like Purulia, Bankura, Birbhum, and North Dinajpur. They have been adversely affected by the fluoride concentration in the groundwater. The maximum permissible limit of the fluoride in the groundwater is 1.5 milligram per liter. If you look into this number, the concentration of arsenic that is allowable is 10 microgram per liter, and in case of fluoride is 1.5 milligram per liter. So therefore, 1000 order of difference between the allowable limit. That means arsenic is more lethal compared to the fluoride. But typically, the fluoride concentration occurs in the groundwater between 2 to some places 20 ppm, 20 milligram per liter. So that is also equally bad. So we tried to look into the how to remove this issue. So remove this pollutant from the groundwater. So if we have done a market analysis and looked into the various existing fluoride removal filters, there are 2 technologies those are existing typically. One is the membrane-based reverse osmosis nanofiltration. Another is the adsorption-based activated aluminum, activated carbon. So the membrane-based filters are very, very expensive. The values, the cost values are given here, and it has the maintenance is not easy, and there will be fouling of the membrane. One has to replace the membrane, and it's a costly affair. Even for the activated alumina based filters, the filter the absorption capacity of fluoride is very less, only 5 milligram per liter. So therefore, it does not last for more than a week. Within a week, one has to do a chemical regeneration. Even now chemical regeneration is expensive. Chemicals are used, and the regenerated fluoride again will go to the groundwater and recontaminate it. So average cost of these commercially available filters are 15,000 rupees for the domestic filter. Now we tried to develop a material for the fluoride removal, and we tried to find out why this fluoride is being is contaminating the groundwater. We have found out there are 4 sources of fluoride leaching and contamination of the groundwater. First of all, like arsenic, fluoride is also available in the rocks in the form of calcium fluoroapatite. So this particular phase is there in the rock where the fluoride is there, and this particular phase will be degraded over million of years because of weathering and other causes, and the fluoride get released and come and contaminate the groundwater. Leaching from industrial waste like aluminium, zinc, and copper industries, there is fluoride which can contaminate the groundwater. Fertilizers industries, where the fluoride is used, again they can leach out and contaminate the groundwater. Toothpaste producing industry also, the effluent that from the effluent fluid is leached and contaminate the groundwater. So these are the typical. There are anthropogenic cost as well as the geogenic cost for the fluoride contamination in the groundwater. Now, what do? We try to develop this the hydroxyapatite group. The when this hydroxyapatite phase is there, when it is replaced by the fluoride, this is known as the fluoroapatite. So we try to develop this hydroxyapatite phase in the laboratory by the simple chemicals. And then what do? This calcium phase removes the fluoride, because one calcium, it attracts the two fluoride atoms, so it forms the calcium fluoride. So then here it produces CaF2, right? So two fluoride atoms. So what do? We carefully substitute some of the calcium by the aluminum. So we call it aluminum substrate hydroxyapatite. So because it increases its capacity several folds, because aluminum attracts three fluoride atoms, and the calcium attracts two. So therefore, if we substitute some of the calcium by the aluminum, its fluoride removal capacity increases. So we develop this aluminum substitute hydroxyapatite phase in the laboratory using commercial grade chemicals. Now this material is produced in the powder form. Now the powdery material cannot be used as a fixed bed for the removal of the fluoride. So what we did, we developed this particular phase in situ with a porous carbon scaffold. Here the porous charcoal, that is commercially available porous carbon we use, and that uses as a support material, where inside the pores and on the surface, this aluminum substituted hydroxyapatite is generated in situ. We call this material aluminum HAP carbon, and this is a commercial production unit where 150 kg per batch is produced, and this can be scalable to 500 kg per batch to even 5,000 kg per batch. So here we do not require any high pressure, we do not require any acid, we do not require any alkali, we do not require any heat treatment. So these reactions they occur at normal temperature and normal pressure after using the commercial grade chemicals, and we will be producing, since we are producing the carbon scaffolds in millimeter size, so they are granules. We are not producing powder. Ultimately, we are producing the granules, and this is the final media that is produced. Okay. Using this media, the filter is the filter is developed. So these are some of the properties. If you see, the total fluid absorption capacity of this media is 105 milligram per gram at 30 degrees centigrade. The nearest competitor is the activated alumina, which has a capacity only 5 to 6 milligram per gram. So almost 15 times more capacity we will be getting from this particular media. So I have given a comparison with other adsorbents. If you look into the powder-based adsorbents, their capacity is always higher. So, but powdery adsorbents, micron size or nanometer size adsorbents, they cannot be used for as a filter media because of the high pressure drop and leaching of the medium. So therefore, we compared this thing with the granular media, and we have found out that among all the granular media, we have obtained the highest ever reported value, that is 105 milligram per gram, which has a particle size 0.5 to 3 millimeter. This is an ideal medium size for preparation of a fixed bed adsorption reactor. Then we characterize the adsorbents from the FESM and EDX analysis. It is clear that there is this is the carbon scaffold I was talking about, and inside the carbon, the hydroxyapatite phases have been generated, and those are the potent sites where the fluoride get absorbed. If you look into the EDX curve, there is a peak of fluoride. There is a peak of fluoride after absorption, which was not there before absorption. So this proves that the fluoride is being absorbed within the media. Phase analysis using XRD and FTIR spectroscopy. This analysis shows the signatures of the presence of aluminum hydroxyapatite and aluminum hydroxyapatite inside the carbon. Then comes the disposal of the spent medium, how we dispose the medium. This particular medium, since we are using the carbon scaffold, this particular medium will be having some calorific value. So calorific value of lignite coal is 6,500 calorie per gram. Calorific value of our aluminum hydroxide AlHC material is 2,200 calorie per gram. So therefore, we can extract some calorific value out of this media. So this media, after its life will be over, it can be used as a fuel. So if we use, if we mix the spent media with the lignite coal in the ratio 1:20, we get a calorific value of 5,000 calorie per gram. The spent media adsorbent is mixed with coal and used as fuel. We have done the analysis. 97% fluoride is in the ash and only 3% is in the gaseous form. So it does not contaminate the environment, and leaching of the fluoride from the ash was less than 1 milligram per liter always. So after its life will be over, this media can be used as a fuel, and the ash will not contaminate the groundwater, number one, and then the gaseous form also, we do not have any fluoride contamination. Now we have prepared the domestic filter as you have shown earlier by this media, and it is a again layer wise media, and this is deployed in different places of Bankura and Purulia district. This is one of the place in his house the domestic filter was there, and it's a more than 1 year data is given. If you look into the feed concentration of the fluoride, it varies. It is around between 2 to 2.5 milligram per liter, and the filtrate it increases. And this particular filter was designed for 1 year. So if you look into the performance, this is below that permissible limit. It is still permissible. It was working fine up to 450 days. Okay. After that, the filter media will be changed. Another community scale filter of 500 liter per day in one of the schools in Bankura district. This filter is running till now. So here you have concentration around 3 milligram per liter, and the filtered concentration is always less than 1.5 milligram per liter. Another school, it has been deployed. It was marginally there. The concentration was 1.5 milligram per liter, slightly above that in some cases, some days, and it is always less than that in the filtrate. So this technology was transferred again to companies, and they come up with 24. By now there are 34 filters have been deployed in different places of Purulia, Bankura district, and now this chart is very important. This gives a filter life. This is a filter life at different locations, and if you look into this, based on the feed concentration of the fluoride, and we have just charged around 80 kg of the material in 2 columns, and we have seen that depending on the feed concentration of the fluoride, the filter life will be varying for 9 months to more than 12 months. So these filters are designed for 12 months, and then after 1 year, the media has to be replaced. One of the domestic filters that have been deployed in one of the houses where their kid is having the dental fluorosis. So let us do a cost comparison with other filters in the market. Now, if you look into the different other filters, so the domestic scale filters are the same capacity, 120 liter per day. So cost varies, above 15,000 rupees, and our cost is 4,600 rupees, around 5,000 rupees for 1 year. And after 1 year, the filter media has to be replaced. For that, one has to have such a recurring cost around 600 rupees. So cost is 1.3 paisa per liter. Okay. So this is the status of this technology. This technology has received the IGCW award by Green Chemistry Foundation in 2023. It is recommended by Fluoride Task Force, Government of West Bengal, transferred to 2 companies for commercialization. Currently, 34 community scale filters are in operation, catering to about 1 lakh people in affected districts per day. Next case study, I'll be talking about the treatment for the rice mill effluent. So in a typical rice mill, there are, depending on the size of the rice mill, one can get effluent to a tune of 50,000 liter per day to 150,000 liter per day. So that much of water is extracted almost every, and they use the same water 2 cycles. That means every week 3 times they extract water from the ground. And just imagine in the district of Bardwan in West Bengal, there are 1,500 rice mills. So just can imagine how many rice mills are there in the West Bengal, and each of these rice mill is extracting 150,000 liter of water roughly per day, not per day, 3 times a week from the groundwater, and how the groundwater will be depleted. Now, the effluent that is generated out of these rice mills, they're high in organics, they're foul smelling, and there is no proper treatment. They just discharge it to the nearby canal. So when these canals go to the water that goes off from the canals, they go to the agricultural lands. There is protest, and the farmers, they often do a road blocking. So there is a proper treatment needs to be required. So what we did, we developed a very simple treatment. We take the water on a feed tank, and then we do the alum coagulation. Since there are lots of organics present in the tank itself, the suspended materials, they get settled more than 95%. Then we pass it through oxidation column, where the rest of the organics get oxidized. Then we pass it through the lateritic column, where and carbon column, where rest of the organics and the ordering material, they get arrested. And then we get the treated water, which is very clean, crystal clear, without any odor. So this particular filter requires a backwashing every 15 days with a 5-minute pulse. So there is simple operation. There is no maintenance required at all. There is no chemical that is involved apart from the alum coagulation, and its life is safely 3 to 5 years. And we can use the reuse of the effluent, the treated water that is generated, that can be reused in the plant itself. So this is a 40 KLD plant, 40,000 liter per day capacity pilot unit installed in Srima rice mill in West Bengal, in Hooghly district. So here the water flows through the a series of columns, and finally this is the raw water, which is yellowish in color, and this is the treated water, which is very clean. If you look into the various parameters, this is the performance for 2 years. It was installed before lockdown, 13 March 2020. Initially, it was 10 KLD capacity. Later on, its performance was so good, it was upgraded to 40 KLD capacity. And at the end of 2 years, it is showing almost steady performance. Economy is yes.
Can I just please? Can you tell me what is the backwash material? I couldn't catch the name. You were saying backwash with some material. You know that previous filter. You said that it requires backwash.
Yes.
What is the material? What is the material?
Backwashing is done only by the clean water. The filtrate, that is clean water, it is being backwashed with pulses of 5 minutes. Okay.
But all the clean water will be used in the backwash, or
no.
Only a small quantity goes?
Small quantity will be required every 15 days.
Okay.
Every 15 days, one has to do a backwashing.
Thank you.
Yeah. The economy is 18 rupees per kiloliter, and typically for a good for the groundwater for drinking purposes, the economy should be less than 20 rupees per kiloliter. For an industrial effluent, it should be anything between 40 to 60 rupees per kiloliter. That is acceptable. So therefore, this also the economy of this technology is also very good. This is a 1 lakh liter per day capacity pilot plant installed in Nilachal rice mill in Bardwan district. Next case study, I'll be talking about the cyanide removal from the steel plant effluent. In a steel plant, there are lots of cyanide steel plant effluent. So these cyanides concentration can be anything between 5 to 20 milligram per liter, and the permissible limit of cyanide in any surface water is 0.2 milligram per liter. So what we do, we did a very simple treatment in presence of UV light and air bubbling. We add the hydrogen peroxide. Hydrogen peroxide dose is 5 liter per meter cube. The hydrogen peroxide gets oxidized, it gets degraded to form the hydroxyl radicals OH dot, and in presence of air, they form finally the bicarbonate bicarbonate salt, and nitrogen gas and water. So what we require to give a hydrogen peroxide dose of 5 liter per meter cube with continuous air bubbling in presence of UV light. So it is a photodegradation technique, but without any sludge generation. So using this technique, we developed a process for the Tata Steel, because we are having a project with the Tata Steel. So if you look into the cyanide concentration before treatment and after treatment, it was up a maximum, it was 15 ppm, but after treatment it was 0.6 ppm. So they came up a plant with a capacity of 5 meter cube per hour capacity in the Jamshedpur site, in the Tata Steel site, and they ran this plant with our technology for 6 months. They developed confidence. They came up a plant at Angul with 80 meter cube per hour capacity, and it was working fine. Since last, so I just mention, I would like to mention one of the shortcoming of this technology. This plant was run for about a year without any problem, and then suddenly I heard that the plant was stopped and not in operation. Then I inquired what is the problem. Ultimately, it came so it is not the limitation of the technology. It is because the hydrogen peroxide they are using in the laboratory, we are using 1 liter, 2 liter, but in the plant where you are talking about a treatment of 80,000 liter of water per hour, the amount of hydrogen peroxide requirement is very high. So therefore, they have to store hydrogen peroxide, and the storage of hydrogen peroxide is not normal, because under normal temperature and pressure, hydrogen peroxide breaks into oxygen gas, and if you do not take proper precaution means one has to sprinkle water onto the storage vessel to keep down the temperature. So if you do not do that, then there will be built-up of oxygen gas after its degradation, and then there may be a blast. In fact, that has been happened because of the not taking the proper precaution. The whole storage vessel that was storing hydrogen peroxide blasted, and there was an accident, and that's why this plant was stopped. But that was not the fault of the technology. That was the fault of the storing of hydrogen peroxide. That means whenever a technology becomes successful even in the real life scale, it is not the technology, it is the other paraphernalia, procedures that have to be followed properly. Next case study, I will be talking about the treatment of refinery effluent. So here we are talking about an effluent of HMEL, that's the HPCL Mittal Energy Limited. They had their plant in refinery at Bathinda, Punjab. So what the problem was in their plant was they're having the standard effluent treatment plant consisting of primary effluent, secondary effluent, and tertiary effluent. In the secondary effluent, they use the activated sludge procedure, and after that they are using the membrane bioreactor as a tertiary treatment plant, and their final objective is to get the water at the final stage of having COD less than 20 ppm. That they are not getting because their secondary treatment plant was not operating properly. The membrane bioreactor, there is a tertiary treatment that was very, very expensive. Membrane needs replacement every year, and every year they are spending 5 crore rupees to replace the membranes for the membrane bioreactor. So they wanted as a simple technology that to remove COD. So our objective was to do away with the secondary treatment process. The secondary treatment is basically the most time consuming. It is very slow, number one. Number two, it is space consuming also. It requires huge amount of space. So that becomes bottleneck in most of the cases. And third most difficult thing is that bacteria that those are nurtured in the activated sludge process for the degradation of the organics, maintaining those bacteria, maintaining the environment for their growth is also difficult. So what we did, we just did 2 continuous fixed bed adsorption using commercial carbon, and we are able to bring down the concentration of COD less than 20 milligram per liter. And we developed a scaled up process flow diagram, which where the first we give the laterite column along with the oxidation medium. then followed by the carbon column. There are 4 carbon columns which will be used to remove this. Then using the fundamental theory, we scaled up this system and we proposed what will be the amount of carbon required, what will be the specification of dimension of various columns required for 2 meter cube per hour, 1 meter cube per hour, and 50,000 liter per day, 10,000 liter per day, and 20,000 liter per day. Okay, so they came up with a plant of 50 meter cube per day capacity at their site, and now they are doing the trial runs with this particular plant. Next, we talk about the treatment of sewage water for reusing. This project we got from Kolkata Municipal Corporation. Here, the sewage water that is being wasted, if we can reduce the parameters to such a level that the water can be used for the road cleaning purposes, gardening, and tree cleaning, etc. So we developed a simple process, and the whole focus was to make the primary treatment and the tertiary treatment so efficient that we should not be depending on the space and time consuming secondary treatment. That means we would like to do away with the secondary treatment process altogether. So we came up with a schematic like this. We do first the feed is stored in a tank. There itself some sludge will be generated, and then we give the coagulant and chlorine dosing to remove the bacteria, and then the sludge is taken to the soak pit. Rest of the water is taken to the various columns filled up with the treated lateralized oxidation medium like manganese dioxide coated sand, and then carbon columns, and finally we get the storage tank from where it can be used for the different purposes. Okay, so I have some data of the results of different locations. So they have given us we have used this technology to check the process for water from 3 locations. One is the Southern Avenue. The standard, this is the standard given, and our treated water is behaving well within the standard. And then so this is the feed water. The feed water is slightly yellowish in color, and the filtered water is clear, crystal clear. Next comes the Mukundapur Canal. This is one of the canal in eastern part of Calcutta, where the feed water is dirty, and we get the clean water, and all the parameters of the treated water is well below the standard limit. Then the Bantala leather complex, that is the most difficult area where there will be chromium. Chromium is there. So here we use the treated laterite to remove the heavy metal chromium, and after treatment we are able to clean this water to the reusable, not for the drinking purpose. This will be used for the road cleaning, gardening, etc. So finally we got they have given us water from 4 locations, and we have optimized the chlorine dosing, and we have optimized the alum dosing, and using these optimized dose. In fact, the primary treatment is very important in this case. We kill all the bacteria by the chlorine dosing, and then we give a settling time of 30 minutes. All the sediments, they get settled down. Then we take the supernatant and pass it through the series of filters, and this is a long-term performance. We have flow rate of 36 per liter per day and 144 liter per day. So this is almost 70-hour operation. So if you see, the COD was 320 milligram per liter of the feed, and the filtrate we get less than 20 milligram per liter. Similarly, even if you increase the flow rate 4 times, so still then you will be getting the almost same performance. That means flow rate is not an issue in this case. So the idea is that if we do a primary treatment properly, then all the tertiary treatment will take care of the other parameters. These are some of the final results for different locations of the plant. At the end of the sand column, at the end of the oxidation column, carbon column 1, 2, and this is the effluent standard, the NGT, National Green Tribunal limits. and it is already always less than that limit. The sludge that is produced is high in organics. It can be used as the manure also. So this is the proposed process flow diagram we have proposed to them, and we have submitted the final report. Now they will just look into it, and it was decided that one plant will be coming up of 50 meter cube per day capacity at one of the locations. The location is also identified. This is near Ruby Hospital, so where it will be installed. Now they will be looking into this, and they probably sometimes this year they will be putting the tender to build up this plant. So I come to the almost end to my presentation. So what is the takeaway? Takeaway is that for a good technology which is of low cost without compromising the quality, we need not to have a groundbreaking invention. We can do innovation, we can do improvisation of the existing technology with an aim to reduce cost, accessibility, value addedness, and performance of the existing technology. And success, what I feel is that success of the technology lies in its outreach capacity and affordability, so that a person who is staying in a remote village and a marginal common map people should be able to afford it, then that will be the success of the technology. And of course, willingness to do something, to take the research to the end. So sometimes we see that we start a research, and when the scholar is getting PhD degree, the research ends there, and the next scholar starts from afresh. It should not be like that. It should be a sustained effort is required, where the 3 to 4 generation of the student may be required to take a technology from the laboratory scale to the field scale. If we look into the time scale, timeline of the arsenic removal technology, which was most successfully developed in our laboratory initially, we started the research in 2004. By 2006 or 2008, we came up with a possible solution. Then we applied to DST, Department of Science and Technology, Water Technology Initiative Division, and we submitted a proposal. The proposal was sanctioned. Then came the UNICEF, and UNICEF, with the help of UNICEF, we came up with a plant, the community scale filter, in 2012. By 2012 and 2015, I gave at least 15 presentations in front of the Arsenic Task Force, Government of West Bengal, to convince them that the results are okay for last few years. Once they were convinced for the looking into the performance of the community scale filter for last 3 to 4 years, then they gave the approval in 2015. Once the approval of the regulatory body was obtained, then the commercial companies, they came for the transfer of the technology. Then the technology transfer happened, and then the community-based filters, they came to the existence. And the first technology was transferred in 2015, 2016. So that is a sustained effort of almost 10 to 11 years were there for develop this technology from the laboratory scale to the plant scale. So I acknowledge various collaborative agencies, UNICEF, DST, Public Health and Engineering Department, NGO partners, various research scholars, staff members, analysis expert of the department, etc. Thank you very much. So if you have any queries, I'll be able to answer them.
Thank you, Professor Shishendu, for your excellent lecture and insight into the development of technologies, and again successfully transferring them to the commercial units for various things. Now it is now open for any discussion, question and answer. Professor Sanat Kumar, are you here?
Yes, sir. I'm here. Can you hear me?
Please. You are the first to start.
Sir, I have a question on the first part of your lecture and in the last part of your lecture. Okay.
Yes.
Now,
yes.
first part, I am an urban householder. Now, in the urban householder, I use a filter which doesn't require electricity, but it seems to have 2 candles. You put the water on the top vessel and it goes through the filter and then comes down to the bottom. So every day we fill, and it's about 10 liters size. Now my question is like this: what is that filter made of? Is it just sand? What is it? That the next one. When do I know that the filter is over? I have to replace that filter. How do I know? These are the two questions on that first one. Second one, the last problem is on the sludge removal you are telling. So now I come from BRC. So anyway, so I have heard that BRC has got a radiation level of treatment of the sludge, and then it kills the microorganisms, and then that is purified. So is that not applicable to you? These are two questions, sir.
Yeah. Number one, for the first question, your filter that you are using in your household, it has two candles, and typically these candles have, in the first candle there is a cloth filter. Most probably there is a cloth filter. So that cloth filter removes all the dirt, suspended material, and iron to some extent. And then the second filter removes the maybe bacteria. I'm not very sure about the constituent of the filter, but typically they should be removing the bacteria. So in a household filter where the municipality supply is there, the most common contaminants are the iron and bacteria. Where from these come also, although they do a pre-treatment before sending to the pipeline, because of the old pipelines, the iron comes, and because of the contamination at some points the bacteria comes. So probably these are the two contaminants, the constituents of the filter, and one of the candle may be packed with the carbon. Okay, so that removes the bacteria and or ordering agents, and the first candle must be having a cloth filter which will be removing the iron and dirt and suspended material. And how do you know the when the filter candles to be replaced? It depends on the quality of the water and the filter performance, of course. So if you one simple thing that one can get, if you have some some metal-like test in water, that means iron is not, the filter is not able to remove it. So therefore it needs to be replaced. Number one. Number two, if the filtrate rate becomes very slow, that means the candles are choked and they need to be replaced. So
Okay.
these are two things that one can do to replace the filters.
Okay.
Regarding the second question about the sludge treatment, whenever we are talking about the sewage water, yes, I know that BARC use the radiation for the killing the bacteria in the sludge, but there are two shortcomings of that technology. That's why it is not widely used. Number one is that whenever you are producing a sludge, it's a huge volume, almost semi-solid volume. So whether your radiation will be really reaching to the core of the volume, that is not very sure. And secondly, it will be definitely expensive. So under normal circumstances, we are not able to use the radiation. Of course, will be killing the bacteria, but under normal circumstances, it is not feasible.
Okay, sir. Thank you. Thank you.
Professor Suresh Patnaik, would you like to raise some question? Suresh,
Yes, sir. Yes.
Please.
So good evening, sir.
Good evening.
I would like to know something that many parts of Odisha also they suffer from this arsenic in groundwater and as well as fluorides. So what I want to ask is that, sir, I'd like to know is that most of the common filters, other than the RO, normal filters, they usually have maximum that activated carbon and things like the cloth type of filters and those, sir. So in using, I don't think they have this laterite or treated laterite layers or even that activated alumina also. So can we, using your technology, can you have add columns of those laterites, treated laterite, and the activated the thing as separate columns or filters,
Yes, yes.
add to the existing ones, and use in the homemade this thing or usual filters. I don't know whether the commercially available ones have that laterite and the activated alumina. I don't know, but if you can add these as separate layers or separate columns, it can be beneficial, I think. So,
Yes,
so
you're
that I would
absolutely
like to
right.
know, sir.
Yes, you are absolutely right. they use the cloth filter and the carbon filter, but you can put the two columns filled with activated treated laterite and means the fluid removal media. And then the water can be used as a normal RO route. In fact, RO is not required in that case. Unless until you have higher TDS in your feed water. In fact, if you know that there's a Supreme Court ruling that if the TDS in the feed is less than 500 ppm, we do not use RO. Because in Kent RO, you'll be wasting around 70 to 75% water that is wasted. So, but these types of filters are basically what if the 10 liter is filtered, 10 liters will be coming out. So there is no wastage.
Sir, is this commercially available, sir? Sir, commercially available, sir? These filters like
yes. These columns are commercially available.
Okay. Thanks.
Okay. So Surya Tejaji, would you like to raise some question?
Yes, sir. Good evening,
Surya
sir.
Tejaji, please.
Thank you for a very comprehensive lecture, sir. And actually, I have two queries, sir, regarding cyanide removal. How recovered cyanide will be handled, sir? And next part is regarding sewage treatment. All the parameters are within the limits, but why the TDS is unchanged or little increased? And the third one is, sir, general question: how can we approach to solve the issue of this rivers or lakes in urban cities? These are my concerns.
Okay, very good. So first, coming to the first question, what is the first question? First question was about cyanide removal. Yeah, in case of cyanide. No, first question was regarding cyanide, I think. Okay, let's take the first cyanide question first. In case of cyanide, we are not absorbing cyanide and then we are removing it. We are basically photodegrading it. We are degrading the cyanide into bicarbonate and nitrogen gas.
Okay.
So there is nothing called recovery of cyanide. It is completely degraded into innocuous product. That is number one. And your observation regarding the sewage is absolutely correct. Our method is not able to remove the TDS, because for removal of the TDS you need two technologies. One is either ion exchange or reverse osmosis. Okay, so in this technology, TDS cannot be removed. It can be reduced to slightly, but it cannot be removed to that extent. Okay, so whenever you will be having a high TDS loading, then this technology, that whatever I have talked about, that will not work. Okay, so that is number two. And number three is that what is the number three?
How to approach to treat urban lakes or rivers?
Yeah, right. So we have worked with the river water also. So using the similar technology, the last one I was talking about, this the river water can be treated and can be converted to the reusable water. And in fact, we have approached the Public Health and Engineering Department of Goa State, and they have come out with an office order that with this technology developed by us should be used for treatment of the Shal River. There are a number of rivers. One is the major river is Sal River, Sal River. Okay, so they have given us they have taken out a office memo that the technology developed by IIT Kharagpur should be used for the treatment of the Sal River. And
congratulations, it's a very big thing.
It's a very big thing. And now there are few companies now that they're formulating a proposal, and we are going to start work in another year to treat the river water from Sal River. So same technology can be used.
Sir, what about Yamuna? Yamuna, they are treating, removing all this dirt. How is that done, sir?
Yes,
very large volume of that's what I see. Foam is there mostly. So what is it?
So what is that? Yeah, foam is basically industrial wastewater. Mostly the industrial wastewater, because all the industries along the Jamuna, they are disgorging the whole effluent in the river itself. So there should be upfront units in the industry where that water should be treated there, and that treated water should be discharged into the river stream. Now, if we put a treatment plant in the Jamuna River itself, then tackling all these foamy material will be difficult.
Okay, okay.
Yeah.
So I'm reminded of, sorry to take one more second.
Yes,
I'm
yes.
reminded of an anecdote in London. Thames used to be very dirty apparently. So they have dug a channel inside Thames, and that is taking exclusively all the wastewater and putting it into the sea somewhere. That I don't know where it is putting, but that is how Thames has become cleaner. Is that correct?
Maybe I'm not aware of that.
Okay.
Any other question? I have actually one very small doubt. That is the RO filter that we are using, whether it is LG or Kent or anything of those type. Why it has got actually 4 candles, and so much water is getting actually wasted?
Yes, yes.
Is it
So,
really wise to use such a
yeah,
filter?
we have opened the Kent RO whole system. So first candle is where they put the cloth filter. Second candle is filled up with carbon. Third
Okay.
candle, they put an ultrafiltration membrane. And the final candle was the reverse osmosis membrane.
Okay. So that therefore actually it is like this.
Therefore, it is required. And the water that is being wasted, it is coming from last 2 candles, not first 2.
Okay. One more small doubt actually what I have is, I am told that let us say in the city of Irvine, they are treating actually the sewerage water to the tune of something like 15 million gallons per day, and converting it to say potable water. Okay. So what is the type of technology such huge installations they use?
Yeah. So basically they use the I think whatever we are proposing in our sewage treatment, they're using similar type of technology, but at the end, at the final step, they're using a membrane, an RO.
Okay.
That will convert the reusable water into potable water.
Okay. Thank you so much.
Thank you, sir.
So, in fact, it was such a great pleasure to listen to Professor Sishan today on very important aspects, like actually the scalable, low-cost technologies for water treatment, not only for the for removal of effluent generated from the rice mills, cyanide removal, steel industry effluent treatment, organic removal from the refineries, and many other things, including arsenic removal and fluoride removal. So, in fact, it is actually his excellent talk which has given the insight that how the research actually has to be done and really take it to a commercial scale, and also it could be really transferred to the household and small communities to take care of actually their needs. It was really a very, very insightful talk given by Professor Day. Of course, Sanat Kumar ji, you have raised your hand. Would you like
No, sir,
to?
no. I wanted to agree with you. Whatever you are saying, I wanted to agree with you. So that's why I said put that.
Okay,
so
thank you.
Whatever
Thank you.
are saying, I'm agreeing with you. Yes.
No. Thank you so much. So, Professor Day, on behalf of the organizing team, I have great pleasure in proposing a vote of thanks for your excellent and emulating lecture, which has opened so many things, and possibly the researcher in this area, they should really aim at how to take how to develop low-cost technologies and how to really take it to a commercial scale and make it implementable. And you have done a great job in that direction. We are very, very thankful for your excellent lecture. Finally, I would just like to ask one small request that do we have your lecture is actually recorded. Do we have the permission to circulate it? If you say yes, it will be circulated. Otherwise, it will not be.
You can circulate, no problem.
Okay, thank you so much. Thank you so much, Professor De. It was such a pleasure listening to you.
Thank you. Thank you.
Thank you. Thank you so
Thank
much. Namaste. Good night.
Good.